Hello, my name is Kevin Pearies. I am a Senior Technical Sales Specialist with EXFO. I have been with EXFO for just about 10 years, but have been in the communication industry for a little over 20. So I started out in construction placing fiber as a teenager and eventually worked my way up into an operator, maintaining and troubleshooting fiber optic networks all over the United States. And so today we'll be talking about something that's very near and dear to my heart, and that is OTDRs. Optical Time Domain Reflectometer. So we'll talk a little bit about what an OTDR is, and then some of the issues that you will have while you're testing. So the importance of connector cleanliness, the importance of understanding the test parameters. Now obviously we won't be able to get into every little aspect of an OTDR, but for this particular webinar I'd like to focus on the interpretation or the complexity of interpreting an OTDR trace, and then showing you some new test software and hardware that really eases that process a bit. Anytime I talk about OTDR testing or any fiber testing at all, I always talk a little bit about Fiber 101. So we're not going to get deep into Fiber 101, but there are some important aspects of understanding how the light propagates down the fiber to help you better understand how to analyze the OTDR test data. And so one of the important things to realize is index of refraction. So index of refraction is the speed of light within a particular type of material. So your base value index of refraction of 1.0 is the speed of light in a vacuum. So that's 300,000 kilometers per second in space. So as you travel through different materials, or as the light travels through different materials, the speed of the light actually slows down. And so when you look at a piece of fiber, the actual fiber core itself is 8-9 microns in size, and it's wrapped around with cladding. So wrapped around the fiber core itself is cladding, and the cladding has a different index of refraction. And so the difference between those two materials is what helps keep the actual light within that core of the fiber. And so this is called total internal reflection. And when the light is injected into the end of the fiber, it actually reflects off of the cladding. And so it's very important for the angle of the light as it enters the fiber to come in at a certain degree. And so they call it the critical angle. You might have heard the term numeric aperture or numerical aperture. So it's basically this cone of acceptance of where the light needs to come in and at what angle for it to properly reflect off of the fiber. And so one way that I like to explain this is if you're skipping a stone on a pond, you'll get a nice flat stone and you'll try to get the angle just right to maximize the amount of skips and to get more distance out of that stone toss. And so as soon as the angle of the stone changes, you take a dive into the cladding. And so the same thing can be said with fiber optics. So if we create a macro bend in the fiber, which we'll talk about later exactly what a macro bend is, we change the shape of the fiber core, and we change the angle of the actual laser, the light reflecting off of the cladding. And so when that happens, that light can leak through the cladding or eject through the cladding, and so we get extra loss. And so we'll point that out. So that's one of the very important things to understand about fiber, is how light propagates down it. It's basically a glass conduit that carries our signal. We talked quite a bit about reflection in the last segment, which brings us to a very, very important thing to understand, that is connectors, or physical connectors. Anytime there's a physical connection in the fiber itself, so connecting two pieces of fiber, we have high reflection. So normally when we talk about physical connectors, we're talking about actual connectors, but certainly mechanical splices can also contribute to some reflection, but to a large degree in this particular tutorial, I'm more concerned about physical connectors. So there are different type of connectors in the system. The actual connector housing itself, and then the actual end face. So there's two things to consider. So your connector housing here in the United States, a lot of companies have standardized on the SC connector, the subscriber connector. So here they call it Sam Charlie connectors. And so with the Sam Charlie connector, it is a 2.5 millimeter ferrule with the square housing on it. And so another common connector is the FC connector, an LC connector, which is a lucent connector, which is a smaller housing, so you get more density out of it with a smaller ferrule. So instead of 2.5 millimeters, it has a 1.25 millimeter ferrule. So it is quite a bit smaller, and something that we see quite a bit more on the optic side of the equipment. So you do get a little bit more density out of that LC connector, or the lucent connector. And so that's the connectors themselves. It's also important to understand the actual end faces. So if I were to grab a jumper here, I have a hybrid jumper. On one end I have a blue housing or blue connector, and on the other end I have a green. So they're both the same kind of connectors. The actual housing themselves are SC. So these are Sam Charlie connectors, but the end face varies. So there are different types of end faces, whether it's going to be a flat cleave, whether it's going to be a PC or a polished connector, like a UPC connector, which is what this blue color code denotes, is a UPC, or ultra polished connector. And this green one is an APC connector, or angled polished connector. So traditionally in the telco environment, a lot of folks are used to seeing the blue connectors, but the green connectors, the APC connectors, have lower reflection, and so that's why most of our OTDRs ship with APC connectors, just to give us that lower reflection, which really gives us much more consistent and highly repeatable results. I first started seeing APC connectors when I did some work with the cable TV companies. And so cable TV companies would broadcast a signal to multiple subscribers. The exact same signal would be broadcasted out. And because of that, they used an RF analog signal. They amplified it quite heavily. So when you amplify a signal, reflection of a connector is a percentage of light that's being returned. And so as you inject more power, of course, your total power coming back, percentage-wise, it's going to be the same, but the total power value coming back is higher, of course, than if it had a lower output power transmitter. And so because of that, a lot of the cable TV companies have been using APC connectors for quite some time. So we are now seeing APC connectors being heavily deployed, primarily due to PON, or fiber to the home type of infrastructures. A lot of companies have standardized on APC and Sam Charlie connectors for PON deployments here in the United States. So it is important to understand that there are different types of connectors out there that have different performance values or different performance specifications. So most connectors today, your insertion loss is about 0.5 dB or better, roughly. And so it can be as high as 0.75 per mating. It really depends on your specifications, but a lot of the companies that I work with are looking for 0.5 dB of loss or less on a physical mating. And so that's just one of the values that we look at. The second value is reflection, or the percentage of light being returned. If I were to take a UPC connector or a flat cleaved fiber, apply a source to it, and measure the reflection, I expect to see about minus 14.7 dB of reflection. And so that is an open, just to give you an idea. And so the higher the number, the less reflection you have. Disregard the negative. So if you disregard the negative, the higher the number, the less reflection that you have coming back from that connector. So if I were to take two blue UPC connectors and mate them together, I would expect about minus 50 to minus 55 dB of reflection. If I had an APC connector mated to another APC connector, I would expect about minus 60 to minus 65. So APC connectors have less reflection. So they are a higher performing connector in that regards. So if you're dealing with amplified systems, the lower the reflection, the better off you are. And so we're starting to see a lot of APC connectors being deployed heavily, particularly in the GPON market. And so one reason why it's important to understand the connectors is anytime you look at an OTDR trace, you need to be able to interpret the data. And so if I see a reflective event, how do I know whether or not that is a good value? I need to know what type of connectors I have in the field. Certainly companies will have a specification. A standard specifications that we see today for a 10 gig network is typically minus 45 dB or better of reflection at a single connection. And so there are some older connectors in the system. You might have an old D4 connector, which is a 2.0, it's a 2 millimeter ferrule. It's an older connector that typically has higher reflection. And so if you're expecting to get minus 45 dB out of an old style connector like a D4 or even worse a biconic, you're probably not going to get it. And so in that event, you've certainly failed, but at the same time it's important to understand what the specifications of that connector are, because if it is a D4 connector or old biconic connector and you're getting a very high reflection, that's probably spec for that connector. And so you can clean it all day long, it's not going to get any better. So it's important to understand the specifications of the individual connectors. So again, for a UPC, we expect minus 50 to minus 55 dB. For an APC, 60 to 65, minus 60 to minus 65 dB of reflection. So those are two values that are important to understand. When I look at OTDR traces, or when we look at OTDR traces later on in this live system, or the live test that we're going to do, I will zoom in on the connectors and we will look at the reflection values, and I think it'll make a lot more sense when you see that. So one more important point. Why is an APC connector better? Because it has an 8-degree cleave. So an APC connector has an 8-degree cleave on the end face of the fiber, as opposed to, say, a UPC, which is more of a 90-degree cleave. And so thinking back to my earlier topic on total internal reflection, remember the stone skipping on the pond? It's important to maintain that angle. So if I were to stand here and bounce a tennis ball off the floor and hit a wall, if I throw it at a certain angle off of the floor, bank it off of the floor, and it hits the wall, if I maintain the power, the angle of return is going to be the same. So I'll be able to bounce the tennis ball off the floor, it'll bounce off the wall, which is a flat cleave, and then I'll catch it every single time. And so it's very important to maintain total internal reflection, that skip or that reflection off of the cladding, but you don't want your reflection to also take advantage of that same critical angle. And so what they do with UPC connectors is, because there's an 8-degree cleave on the end face, when the signal bounces off the cladding and hits that end face, because it has an 8-degree cleave, it's going to change the return path. And so it's basic pool table or billiards physics. And so when I bounce that tennis ball off the floor, if my wall has a slight degree of an angle to it, it's going to change the return path. So I'm not going to catch the ball. And that is why, to a large degree, APC connectors are better and have lower reflection, is because we change the angle of return on the reflection. And so it'll hit the cladding at a different angle, and then it'll leak light or lose light through that cladding because it's no longer maintaining that acceptable skip off of that cladding. And so anybody who's ever done any OTDR troubleshooting, if you crush a fiber, say mid-span with a backhoe or something, and you shoot an OTDR trace, you expect to normally see a spike if you have a termination panel on the far end. If it rounded off, so when I was a splicer, if I saw the fiber round off, that was an indication to me that I might have an open. And so when you crush a fiber, what do? You shatter the end face. And so just picture that same tennis ball bouncing off of the cladding, hitting that rock wall, and just reflecting in a million different directions. And so that's one reason why you would see it round off on a damaged connector or a damaged fiber. So I want to talk about, or I actually want to show you some of the things that I've talked about. What connectors look like on an OTDR trace, what a connector end face looks like with a video inspection probe. And so I will be using the FTB-1 platform, the EXFO's FTB-1 platform. So this is the platform here in the front, and then on the back is a module. And so the module that I'm using today is the FTB-730. And so this particular unit has an in-service OTDR port as well, which is why you see the second port. But today we'll be primarily using just the standard OTDR features, along with some of our advanced IOLM application, which we haven't covered yet, but we'll talk about here in a bit. And so this particular unit is my actual demo unit. So I'm in my home office. right now. So I do work in the field, and this is the unit that I do use in the field pretty heavily. So it's used and abused in a good way, and so this is the unit that I use on a daily basis when I'm with customers. So we'll be using this particular platform and this particular hardware, and I'll plug it into my network here. And so basically what I have here, you can't see it because it's off to the sides, is I have 2 network simulators and a couple of launch bags. So to my left I have a point-to-point network with multiple splices, reflections, connectors, macro bends, and a lot of other things going on within this network simulator, but it is a point-to-point system. Over to my right, I have a GPON, or actually a PON network simulator. So it's a passive optical network simulator. It has a 1x32 splitter on one side, and I believe a 1x8, a daisy-chained 1x8, so 2 1x8s daisy-chained together. So we'll be able to see what the traces look like on a standard point-to-point as well as a PON system. And then I also have 2 launch bags that I like to use to plug into the network simulators, so I have a connection to manipulate mid-span or somewhere in the span. And so that's what we'll be testing with today. Again, it's the FTB-1 platform with the FTB-730 IOLM module, so in this particular situation. So now it's time to tie in some of the things that we talked about. So I went ahead and took my my OTDR and normaled it back up to my launch cable and to my network simulator over here to my left. So it's on the point-to-point network. I know what's in there, and I know what's what sort of events I'm expecting to see. And but before I do that, I want to be able to make sure and inspect and clean the connector before I plug it in. I've already done that to save some time, but I wanted to show you what it looks like, what a connector looks like on a launch cable. So I'm going to go ahead and launch the fiber inspection probe software on the platform. So I have a handheld fiber inspection probe here. This is a 200-400X version. So keep in mind there's a little bit of delay between the platform and the actual OTDR itself, because, or rather between the platform and my my streaming video. So I am VNC'd into this platform over my Wi-Fi network here at home. So there's a little bit of a refresh delay going back and forth between it. But on the actual platform itself, it is very much real time. So I'm going to go ahead and just plug in a connector that I have here. And so you can see what it looks like on the end face. So that's 200X there. And of course, or I'm sorry, that's 200X there. And then that's 400X there. That dark portion is actually the cladding. You don't see the core, but if I get the light just right, there it is. You can see the core. So the core is that 9 micron in the center there. Human hair is about 40 to 60 microns. So human hair is about 4 to 6 times larger than the core size of single mode fiber. So just to give you an idea of how small it is. So it doesn't really take much to contaminate a fiber. I always like to show this example. I rub it on my nose and then you can see what it looks like. And so we have quite a bit of oils and whatnot on the end of this fiber. So, and if I were to do a pass-fail on this fiber right now, it would clearly fail. So I'm going to go ahead and do a pass-fail capture on this one. So I'll go ahead and run connector max. So basically it's just analyzing the interface of the connector, measuring the size of the particles and in what zones, and then comparing it to an IEC standard. So in this case here, obviously we're getting a lot of fails. And so if I look at the results, we can see the size of the particles and in the certain zones and what it looks like. So it's really important to be able to inspect your connector. If it's clean, then connect. If it's damaged, you want to see that. You want to know it and replace it accordingly. So that's what the end face of a connector looks like. I won't spend any more time on that. So I'm going to go ahead and launch the OTDR software. I want to show you what a connector looks like. So we talked about some of the reflection values that we expect on a connector. So I'm going to go ahead and just shoot a quick auto trace, only at 1550, just for the sake of time. So I'm going to go ahead and hit start. The OTDR is going to determine what it thinks is the best settings. It's going to do distance, pulse width, and time. And so distance is how far you want to test. And the thing is that you want the end event to fill the display, but you still want to see the noise. So you want to see the entire trace and then the noise. And so in this case here, it shows 20 kilometers for the distance. So you see the end spike is all the way to the right, and I can still see the noise, and that's what I'm looking for. An OTDR sends pulses of light down the fiber, How it determines when to send the next pulse depends on the length of the fiber. So when you set it at 20 kilometers, it will time the pulse based on a 20 kilometer span. And so if it's too short, if the end spike was in the middle or to the left, the pulses would not be timed properly, and you'll start getting some ghosting or some false events. So it's very important that you fill the screen and see the noise. Pretty much a no-brainer. Pulse width is the length of the pulse. An OTDR will pulse light. The longer the pulse width, the more power. So the further you could test. But at the same time, the longer the pulse width, the worse the resolution. So if you have a shorter pulse width, you have better resolution. In this case, it used 100 nanoseconds. And then the last setting is time. How long do you want to test? When I was a splicer, it was typical to run about 3 minutes. But nowadays, it's usually 15 to 30 seconds on the average. I don't often see a test run much longer than 45 seconds. And so in this case here, we shot at 15 seconds. We have a nice clean trace. I'm happy with that. And so I'm going to go ahead and show you what a connector looks like. So at event number, I believe it's event number 10 here, I do have a connector, and it's about 500 meters from the end. This is actually this Sam Charlie, so this subscriber connector, green APC angled polish connector. And so this is my 500 meter launch cable that I put on the back end of the network simulator, so we have something to look at. So in this case here, I know what kind of a connector it is and what the end face is. So for this type of connector, again, I expect 0.5 dB of loss and about minus 60 to minus 65 dB of reflection. So if I look at it, I have 0.3 dB of loss and minus 67 dB of reflection. So I'm very happy. So this is a nice, good connection. And so this is very important to understand. When I ran an OTDR as a technician, I always used it to find the backhoe sticking up out of my cable. What I never used it for was to find a dirty connector or a bad connector. And I have to tell you, most of the time that I spent maintaining a system was chasing dribbling errors because of a dirty connector somewhere. And if you're working in a large telecom hotels with a lot of customer handoffs, you might have a lot of tie cable connections. It's not unusual for some of these larger locations to have 8, 9, 10 connectors before they even leave the building. And so imagine chasing that trouble all day long. In this case here, I shoot an OTDR trace, and I would find the events, the reflective events that have the highest amount of reflection. And so in this case here, there's one over here that has minus 43 dB of reflection. I would probably address that connector first for cleanliness than I would this other one at minus 67 dB. And so it's really a great way for you to identify your connectors and which ones are giving you problems. And so in this case here, this is a great connection. I'm going to leave it alone. I'm going to zoom into that connector, and here's what it looks like. It's wonderful. Another issue with connectors is dead zone. After every reflection, the OTDR is blind for X amount of distance. In this case here, if I go to my measurement tab, I have roughly 24 kilometers, or 24 meters rather, of dead zone. So after this connection, when that OTDR pulse hits this connector, it doesn't measure discretely any events for 24 meters. So that means if I have a splice or a pinch within that 24 meters, it's still going to measure the loss of that event, because we know what the power is coming in, we know what the power is going out. But because of that large dead zone, the pulse hasn't recovered in time, so we don't see or discretely measure anything within that dead zone. And so in this case here, it's about 24 meters. And so within this network simulator, we actually have two connectors that are very close to each other. So I'm going to go ahead and select this particular event at 8.6 kilometers roughly. And if you look at that symbol at the left, you have that sideways M. That means that there's a merged event, meaning the OTDR software detects two reflective events close to each other, but cannot separate them to measure the attenuation or the loss of each of them discretely. So I'm going to go ahead and zoom into it, and here's what it looks like. So you can see, we could see the two humps there, the two reflective humps. So we identify that there's probably two connectors there close to each other. If I turn on the measurement tab and then move my marker over, I have a connector about 29 meters apart. So after that first connection, there's another connector about 29 meters away. The problem is that there might be a lot going on there, so I don't know if all my loss from this particular location is coming from the first connector, the second connector, or something in between. So if I were to go back out and zoom, lock my markers in, this is what my dead zone is. You can measure dead zone with an OTDR. In this particular case, I have 75 meters of dead zone. That means from that first panel, from that first reflective event, I'm not discretely measuring any events for 75 meters. There's a lot going on in 75 meters, particularly close to a connector. And so because of that 100 nanosecond pulse width, I'm not able to separate the two wavelengths. So if I drop the pulse width down, that should drop the power down. When that drops the power down, that should improve my reflection dead zone and also give me better resolution. So I'm going to go ahead and do that. I'm going to zoom out. I'm going to go from 100 nanoseconds to 50 and start a trace. So I'm shooting a shorter pulse width. It'll take a little bit longer for the trace to average out because less power on a distance like this, I'm going to have a little bit more extra noise. I'm going to go ahead and stop it here. I'm going to find that same event at 8.6 kilometers basically. Zoom in. I'm getting a little bit tighter peaks. I'm getting a little bit better separation. My dead zone now is 86 meters. So I mean, I still have a substantial amount of dead zone here. So I'm going to go ahead and drop this down to 30 nanoseconds and retest. And this is basically how I test with an OTDR. I'll shoot it in auto mode. I'll determine what, that the distance is right and the time, because those two are no-brainers. Then I'll keep dropping the pulse width down until I get a noisy trace. So look at this trace here. After 15 seconds, I have quite a bit more noise towards the end there. So if I go ahead and highlight that same event that I had before at 8.6 kilometers and zoom into it, look at this. We're able to separate the two peaks now. They're the two reflective events using a 30 nanosecond pulse width. So with a 30 nanosecond pulse width, I'm able to see that the first connection has 0.15 dB of loss and minus 45 dB of reflection. In a 10 gig system, I would be happy with this, particularly with a UPC connector. This would be fine. I would leave it alone. This is my bulkhead, or the bulkhead to say the front side of my tie cable. If I go over here, 28 meters away, I have another reflective event. And so this particular one has 3.5 dB of loss, which is clearly a fail, and minus 43 dB of reflection. So the reflection is too high and my loss is too high. I would address this point first. And so this is where an OTDR really starts to see its value, is to help you reduce your mean time to restore or mean time to repair by allowing you to troubleshoot appropriately. Because typically what you'd end up doing is just cleaning fibers or swapping cards until the system starts working again. In this case here, I know there's something wrong. So the last thing that I want to talk about as it relates to pulse width is resolution. So I've mentioned resolution a few times, but really didn't get into any details. So with an OTDR, of course, as you pulse light, the shorter the pulse, the lower the power, so the less distance you'll get, but the better resolution you'll get. So basically how close up the events can be when you measure them. So with our OTDR, when you set the pulse width at say 5 nanoseconds, that's about a half a meter pulse. And so you're measuring in half meter increments. If you increase the pulse to say 100 nanoseconds, or even 20 microseconds, for instance, 20 microseconds is a very long pulse with a lot of power that will get you a lot of distance, but at the sacrifice of resolution. So at 20 microseconds, you're looking at about 2 kilometer pulse. And so to kind of put this into light, when I was a splicer or work in disaster recovery, it wasn't too uncommon for us to have to use a patch or a throw cable to splice a damage. And so if we had an auger that damaged our cable, we would come in with a fairly short throw cable, say 10, 20, 30 meters long, with splices on the end of that. And so we would basically use that throw cable to patch out our damage. So we had 2 splices or 2 splice pits that were very close to each other. If it was far enough out that we had to use a long pulse width, it was very common for us not to see both events. And so that's one of the issues you run into with pulse width and resolution. So it's just something to keep an eye out for. So up to this point, all the testing that I've been doing with the OTDR has been at 1550 only for the sake of time. But really, you need to shoot multiple wavelengths. So most OTDRs, most single mode OTDRs will shoot at 1310 and 1550. There's other wavelengths as well, 1625 or CWDM ITU specific wavelengths. So there's a lot of wavelengths that are possible. But traditionally, or typically, we see 1310 and 1550 being the de facto standard for a lot of folks to test single mode fiber. So in this case right here, I'm going to go ahead and select both 1550 and 1310, and I'm going to shoot a quick auto test of both wavelengths. So what I ended up doing was daisy chaining my two launch cables together because I want to focus on macro bending as it relates to the different wavelengths. And so in this case, we're shooting 1310 first, so it's going to go in for 15 seconds and shoot 1310, and then it's going to come back in and shoot at 1550. And so there's 1550 shooting right now, and it'll overlay the two traces. I'm going to go ahead and stop it. So what we're looking at here now is you see the two traces overlaid on top of each other. They're fairly flat, they're fairly parallel to each other, and this is what we expect. 1550 should have less loss than 1310. So if you look at 1 kilometer of fiber, that's approximately 0.20 dB of loss per kilometer at 1550. At 1310, we're looking at about 0.33 to 0.35 dB per kilometer. So there's substantially more loss at 1310 than there is at 1550. So we expect to see lower values at 1550, not just for the coefficient or the section of fiber, but also for individual events. So a connector at 1550 or a splice at 1550 should have less loss than 1310. If it doesn't, then there's an issue there, and that's what we're going to address right now. So in this case here, I have a connector. It's our favorite connector here. So in this case, it's about 500 meters out. At 1310, we have 0.26 dB of loss, minus 61 dB of reflection. Great connection. I go to next trace. At 1550, we have 0.30 dB of loss and minus 65 dB of reflection. So we actually have more loss at 1550 than we do at 1310, but it's a very small delta. I probably have a pinch somewhere here in my network. I'm not going to troubleshoot it right now, but the idea is that 1550 should be a little bit better. I'm going to stick with this number right here. I'm all right with that. So what I'm going to do is I'm going to go ahead and shoot another trace, but I'm going to pinch the fiber and create a macro bend. So I'm going to go into the OTDR. I'm going to have it do something that it doesn't like to do. I'm going to have it look through a connector or look through a substantial event loss. So I'm going to go ahead and pinch the jumper at this location. And so that's that location event number 2 on the display there. I'm going to go ahead and auto up again and then start a test. And so I have this pretty substantial pinch here. And so of course we're going to test 1310 first, and I expect to see some loss here. And there is a little bit of extra loss there visually that I can see. So go ahead and let that finish up. And once 1310 is done, of course 1550 will shoot next. And so it's counting down, and now we're shooting 1550. So 1550 is a longer wavelength. And we see a big drop at the center of that fiber. So at event number 2, we see a pretty substantial drop there. I'm going to go ahead and stop the test so we can read the results. So at 1550, or at 1310 rather, we now have 0.6 dB of loss, which is a fail, but it's not that bad. A fail if you're using the 0.5 standard. Some folks like to go with 0.75 on a mated pair. In that case, this would be fine. I go to next trace. 1550 has 5 dB of loss. So essentially I have an attenuator in the middle of my system for the longer wavelengths. The longer the wavelength, the more issues you're going to have with pinching or macro bends in the fiber. So if you're running L-band wavelengths up into the 1600 region, you're going to see even more loss at say 1625 or 1650. So it's important to understand what macro bending is and why you're testing both wavelengths. So when I was a splicer, because the traces back then took 3 minutes, we shot everything at 1550. If it failed at 1550, we would shoot it at 1310. If 1310 failed, then it was a bad splice. But if 1310 passed and 1550 failed, it was a pinching issue or a fiber management issue. Could be a zip tie that was too tight. It could be poor management inside the fiber tray. It could be a pinch in the FDP. It could be cable racking. It could be a lot of different things. And so being able to determine that it's not a bad splice, but bad fiber management or placement is very, very important. You don't want to break a splice if it's not bad. So in this case here, I would go to this location that's 500 meters out. I would look for a pinch in the fiber. And so it is important to shoot multiple wavelengths. If you're on a very long span, like an ultra long haul span, you might use 1550 and 1625 instead for ultra long haul wavelength testing. And so I'm going to go back in here and pinch that fiber again, and I'm going to switch to real time. So I'm going to turn off 1310 and just stick with 1550. And I'm going to go ahead and just use the same settings that used before. In fact, I'll bump the pulse width up a little bit. I'm going to go to real time. So I'm actually going to shoot a real time trace. I'm going to go ahead and hit start, and I'm testing now in real time mode. And there's my pinch. If I increase the power, it cleans up a little bit, because real time is noise. It doesn't average out, obviously. So in this case here, I'll leave it at, say, 50 nanoseconds, and I see my pinch there. I would go to this location, or I would send somebody to that location to manipulate the fiber while I'm testing in real time. So as soon as they remove that pinch, it should show on the OTDR trace instantly, and then we're able to resolve that issue. And so real-time testing is very important and very useful for this type of functionality, for troubleshooting real-time macro bend issues. So testing both wavelengths to determine there's a macro bend, and then using real-time to find that macro bend is pretty useful. And so that's one of the great functionalities of an OTDR. And so I'm going to go ahead and stop that test. And one important point, keep in mind that in a macro bend such as the one that I put in the fiber here, this could be sitting in your FTP tray. This could be sitting up in the raceway inside your central office. If you have an active system that's running and working with a pinch in the fiber, that is basically an attenuator. It's a pad. If you remove a pad or attenuator from a system, you're going to introduce power. So this is about 5 dB of attenuation according to that previous OTDR trace. If I remove that pinch, I've just contributed or added 5 dB of power to the system. You can cause an outage from too much power. And so keep that in mind when you see a pinch in the fiber. It's important to characterize your fiber before a system goes hot. But unfortunately, there's a lot of fiber in the ground today that have macro bend issues that have been in there for 10, 15, 20 years that have been running short wavelength systems like 1310. As soon as you start to need to amplify or to add distance to a circuit, or if you need to go to DWDM, you'll start looking at the C-band and L-band windows, so your 1550 and up stuff. And when you do that, that existing pinch that's been in a tray for the last 15 years will now become a problem. So it's important for you to identify what a macro bend looks like on an OTDR, how to troubleshoot it, how to isolate it, and how to resolve that issue. So I'm hoping over the last 30 minutes I was able to show the value of an OTDR. It really is a critical troubleshooting tool to isolate problems in a network, not only to locate a damaged cable from, say, a fiber cut, but to also identify those intermittent problems from a dirty connection or from macro bends that have been causing you problems. And so hopefully I was able to show that value, and also at the same time, the level of expertise that's required to understand that information. And so most of our technicians don't use our OTDRs very often unless they're fiber splicers. Usually the OTDR is brought out when there's a fiber cut, and hopefully that does not happen very often. But at the same time, it can be a valuable tool that can be used much more often to troubleshoot those intermittent, persistent issues or chronic issues that have been that your network has suffered from over time. And so today there are a lot more technicians that are touching fiber. When I was a technician, it was primarily backbone and trunk cables that were fiber optic. Nowadays we're running fiber to the home, fiber to the curb, fiber to the node, even fiber up the antenna now. And so with this explosion of bandwidth demands, the placement of fiber has really grown exponentially. And so what EXFO's done to help with some of that expertise is to create a software suite and some hardware tools called IOLM, or Intelligent Optical Link Mapper. And basically what it does, it uses the OTDR hardware in a revolutionary way. It'll take multiple traces, multiple acquisitions, so different pulse width, different resolutions. And so with varying pulse widths, you're looking and shrinking and growing the dead zone. With the different pulse width, you're looking at different resolutions with different ranges, and so it does that, and it also runs an algorithm on top of it to analyze that data. And so what I'm going to go ahead and do is I'm going to go ahead and show you what IOLM looks like and how it works. And so within this same platform, I have the option to instead of running OTDR, to do IOLM. So I'll go ahead and start the IOLM GUI, and so it'll come up. And so IOLM, you create these configuration files for different types of networks. So I have my point-to-point to the left and my GPON or PON network to the right here. And so for those two different networks, I'm going to have different specifications. A PON network, or a passive optical network, is a point-to-multipoint network that has splitters. And splitters will have a high amount of loss. So you need to tell the OTDR that it is testing through a splitter. And so within this device, the first thing that you would do with IOLM is you would create a configuration file, and you would set up the different elements for pass-fail thresholds. And so in this case here, if I manage my point-to-point network, I can look at my pass-fails for the individual elements. So in this case here, max splice is 0.15 for the different wavelengths. Connector loss is 0.5 or better. So once these values are inputted in the system, then you're good to go. And so you would create custom configurations based on your needs and your network. So in this case here, I'm just going to stick with point-to-point. So I'm going to go ahead and select the type of test I'm doing, and this is going to be point-to-point, so I'll go ahead and hit OK. I'm going to go ahead and normal this back up to the way I had it before. So I'm going to go ahead and plug this back in here, and then plug this back into the OTDR. So I know I didn't clean the connector, but for the sake of time, I'm just going to go ahead and normally back up. That's a luxury I have working for the manufacturer. And so once I've selected my configuration file, I will select my wavelengths, 1310, 1550. In this case, if I have any launch cables to null out, I can do that at this time as well. And once that's done, there's no distance, there's no time, there's no resolutions. I just go ahead and hit start. And so what's going to happen is the software is going to start with 1310 first and start testing. It'll shoot multiple acquisitions depending on the fiber length. And so this will change. The intelligence of the software will know how many traces it needs to take, how many pulse widths it needs to use, and then it'll do its secret sauce math on top of it. And so you can see by the display it looks a little bit different. And so this is much more user-friendly as far as interpretation goes. Just network block diagrams that everybody's used to today rather than the graph. And so this is great for those technicians that have not used OTDRs in the past, or for those engineers that analyze OTDR data and all they want is just numbers. And so here we are, we're testing 1310 first, so it's about halfway through there. And you'll see the elements, so these different blocks up top, you'll see them come and go. Because as the OTDR shoots multiple resolutions, it's seeing events and then removing them as it sees fit based on what it believes is a real event. And now we're shooting at 1550, so it's going to go through there and do that as well. And so these are all color-coded. So red would be a fail based on the configuration setting that I had set. And you can also notice these little icons here. So at 6.3 meters, I have what looks like a connector icon. So it's telling me there's a connector at 6.3 meters, and there is. And so that's the connection into my my network simulator. And so once it finishes up, it'll give me the results. And so what this is doing is, if you were to try to do this with an OTDR, you would have to take many tests over both wavelengths and then overlay and analyze the data bit by bit. And there's still portions that you're going to miss because you just don't have the ability to look down into the noise like we can with IOLM. And so in this case here, as I click on every different element, it'll give me that information for that. So at 36.5 meters, I have a connector. And that connector has 1.3 dB of loss at 1310 and 1.0 dB of loss at 1550. And then there's the reflection values. And so as I cycle through there, if there's any actionable items, it will tell me that. So down at the bottom, you can see at 38.9 meters, it tells me the connector or bulkhead is damaged, dirty, or not well connected. Inspect and clean as needed. And so there's actually actionable items for you in there to help. So the interpretation part is removed to a large respect. So as I scroll across, I can see all the different events that I have in my network simulator. So here's an interesting symbol. This is a macro bend. So at this location, it tells me to inspect the fiber in this area to search for excessive bending or compression. And so the beauty of this software is, if you remember with the OTDR, we had to shoot multiple pulse width. We had to go from 100 nanoseconds to 50 nanoseconds to 30 nanoseconds to be able to separate those merged events. IOLM gets around this by shooting multiple acquisitions and then comparing them and finding those discrete events that are buried within the dead zones, that are buried within the resolution issues of the pulse width. And on top of that, that analyzes the information based on the parameters that you gave it. And so this is more than a simple linear trace view. So we have a linear trace view with our OTDR that takes the event table and applies a linear trace view that's block diagrams based on that one single shot. What this does is it does a comparison over multiple traces, multiple acquisitions, and it gives you the most comprehensive view of a fiber that you can get. And so the beauty of this is, when I worked disaster recovery, one of the biggest problems we had that extended our MTTR, our mean time to restore, mean time to repair, was fault isolation. By the time the technician got on site, ran the OTDR, isolated the fault, we were well into our 4 hours of our contractual MTTR to our customer. And so during disaster recovery outages, we realized that one of the things that always hung us up was a technician who didn't know how to run an OTDR. And it wasn't the limitation of the technician, it was just they do not use the OTDR regularly enough to maintain that level of expertise. And so we would have somebody on the phone during this disaster recovery outages just to manage the technicians and walk them through the testing. And so the thing with an OTDR is probably 90% of the technicians out there do not get anywhere near 100% of the use out of the OTDR. Only because it is a tool that requires a lot of expertise and a lot of experience. But what ILM brings to the table is it allows a large percentage of the technicians out there to get almost 100% of the value out of a trace. So when they plug into an FTB panel during an outage and they press start, there's a high level of assurance that the information that comes out of that OTDR is valid and accurate. And so with the analysis on top of it telling you what actionable items there are, if there's a pinch in the front panel, if there's a macro bend in the first bolt splice outside the building, it will tell you that with a high degree of accuracy. We'd like to thank you for spending the last 45 minutes with us on this technical webinar. This is the first of a series of new webinars from EXFO, and we hope that you found the information valuable, and we look forward to your comments on the forums and your emails. Thank you very much.